Hello, everyone. So today we have a pleasure to have this presentation, a few stories about virtual machine introspection and malware monitoring. My name is Michał Leszczyński. I work as an IT security engineer at CERT Poland. It's a national CSERT team. And I'm doing mostly the malware analysis tools and infrastructure development. And from time to time, I'm breaking or auditing or fixing web applications. And today I'm going to present together with my colleague, Adam.
My name is Adam Kliś, nicknamed Bonus, and I'm still a software developer at heart. So at CERT Polska, I make automated tooling and systems for malware analysis together with my friend Michał. And in my free time, I like to play CTFs with my team, P4.
Okay, so let's start from scratch. Basically, if we would look at how malware looks like, so we have some family of malware samples, and very usually there is a case that a single malware core or single type of malware is very often packed with many different packers. So basically, we have a single malware family like TrickBot, and the code is the same for many samples or very similar, but the samples are packed with many different strange packers, which makes it very hard to perform a static analysis. So basically, we have a bunch of samples that are somehow obfuscated, and we want to extract the malware core out of it in order to have something useful, right? Yeah, why we would try to extract this malware core? As I said, it turns out that inside of what's packed by these packers, there is very often the same code, so we could have an easy identification, for instance, using Yara rules, and also easy data extraction. So we could easily extract all the hard-coded CNCs and other features of the malware static configuration. Yeah, so how we are doing that on CERT-PL? Our malware analysis process is strongly focused on the topic of malware unpacking, and we simply want to extract some interesting stuff out of malware samples that we receive. So the flow is that we have an executable, then it goes to the sandbox, and then this sandbox makes memory dumps, and these memory dumps again go to some strange strange process that is called identification and data extraction. And finally, we get a JSON with all the information extracted. So in a simple words, we can say that we are converting executables to JSONs describing what kind of malware family is it, what CNCs are hard-coded, etc. And this is how it could look like on the example of Emotet. So we received a sample that was believed to be an Emotet malware, very popular and very dangerous malware that was spreading, I believe, mostly through phishing emails. And yeah, we got a packed exe. It got through our sandbox and through the data extraction process, and finally we have this JSON that tells that this malware family was Emotet. And basically everything that was hard-coded in the sample was extracted here. So we have all the URLs, all the CNCs, also some public key that was used for a communication, and some other keywords that were involved somewhere in the Emotet process. The process of how this malware acts. So some of these keys are relevant only when you also read the analysis of the malware. We have an article on SearchPL, and yeah, so basically everybody knows what is exe and what is JSON, and this magic step in between, right? Memory dump. What is memory dump, and how do we make memory dumps? So I believe that this is a logical dump of memory at the given point of time. It is also very important to record some metadata together with the memory dump. So the base address where the dump was made, this is very crucial. I mean the virtual address, and what was the reason that the dump was made. So for instance, a malware made some interesting API call at this particular moment. So we are making memory dump because we are believing that this malware is already unpacked. So maybe, yeah, we will find the unpacked executable inside the memory dump. And yeah, the profit of this very tedious process is that we get an unpacked malware, or at least sometimes. So the theory about dynamic unpacking, a little bit of theory. In order to have a good memory dumps, we need good heuristics, and to have a good heuristics, we need a good behavioral monitoring. This is what I believe. So since we need a good behavioral monitoring, why can't we just use an ordinary sandbox? So okay, we were using them, but there were many problems around them.
And we can start with the simple ones, and then we'll go down to the more problematic things about using simple sandboxes that were available. The first one is, you may think that hooking some functions like virtual protect might be a good idea, but the problem is the virtual protect is just a simple wrapper around a syscall. And in example of this trick bot, malware can just directly call the syscall with a sysenter instruction and completely bypass hooking, the hooking of this function if you try to do it at the user mode level. Another example of this could be remcos, which this is a bit longer of an example. We can see that Cuckoo Sandbox hooks functions from NTDLL by overwriting its first bytes with jump instruction, with the jump opcode, and then the address of the function we want to call. The problem with this is that some malware realized that this is happening, and they managed to bypass it by simply unhooking those functions manually during runtime. Here, this is a disassembly and decompilation of the sample. We can see that the malware is doing binary match on the first export. Then it loops over all the exports in the table, and then override the 5 bytes to ensure that even if Cuckoo Sandbox or other sandboxes attempted to override the first instructions, they are unhooked by replacing them with original data. And this sample in particular was unpacked by Nazyvam, one of our malware reverse engineers. So we decided to write our own malware monitor. And we had basically 3 choices. We could do this user mode, which we almost instantly crossed out because of the problems previously mentioned. We could do kernel mode, but that was already done by the Cuckoo 2 team, and we wanted to be a bit more original. So the sandbox option was chosen, the hypervisor option was chosen. It was a daunting task, but we quickly realized that the fundamentals are already pre-existing Dragwolf and the libVMI systems were pretty much exactly what we needed to construct our sandbox. At the core of this sandbox lies the libVMI in this case, but overall virtual machine introspection. This is a very complex topic, which very simplified allows you to read and interact with the virtual machine. And it does magic stuff. And this is an example. You can call just a simple program, and it lists the processes running inside a VM by reading its memory. To fully allow us to use this power, we have used the Dragwolf framework, which is a black box binary analysis system. Long story short, you can call it S-trace for virtual machines. This is an example of what you can expect when running Dragwolf. You can see a syscall being logged with all the information you would need. This is achieved by pausing the machine, by putting breakpoints, actually shadow breakpoints, with which the virtual machine is unable to see or interact with or detect. But for us, this allows us to put callbacks to our host machine anywhere if something interesting happens in the VM. So if we have S-trace, what else do we need, pretty much? Well, we have event tracing on the Windows kernel, and we are stealthy because like the shadow breakpoints are pretty well hidden in this case. But we still need memory dumps, and we still want to have stuff like user mode hooks. For example, crypto API is not a syscall, but we still would want to have a key that malware generated. And this is a story where, and for this part, my friend Michał will talk you through.
Okay, so let's start with the memory dumps, how to make memory dumps. So, as I said before, we need to dump interesting memory regions at interesting points of runtime. And in order to accomplish that, we already had an existing fundamentals, which were Dragwolf features. So we could make stealth hooks on system calls and a little bit more even. And libVMI features, so we could inspect the memory of the virtual machine at low level. So we could write, read, and interpret guest kernel structures. So we basically have at least a little bit of understanding what is happening inside the guest VM's kernel, but we have no clue about the guest user mode. We will talk about this a little bit later. So, okay, how to make a simple heuristic that would catch something interesting on the system call level, which we already can hook using Dragwolf. So, for instance, we could have something like anti-protect virtual memory, and this is usually called with some process handle, which is very often pointing to like my process itself, the caller, and the base address, the starting address of the region we want to change the protection settings. And the algorithm is simply look at the memory under the base address, look at the first 2 bytes, and check whether these bytes start with MZ. If so, probably this buffer contains a portable executable, so we want to store it to the hard disk. This sounds very naive, but it actually works pretty good. And even if the malware guys would patch the MZ thing, which is pretty easy to to patch and overcome, we could check some other features of portable executable that are not that easy to patch or overcome. And another example of heuristic, so we could hook NT free virtual memory, and basically we could look at the memory that is about to be freed. So we could easily, while being in the kernel mode, we could easily look at things like page table entries. So we could check the page table entry at the first page that is under the base virtual address, and we could check whether it's valid, writable, executable, and all of these three at the same time. So if it looks so, then it also looks like a malware, or at least something interesting, because usually normal programs don't have both writable and executable pages all at once, except legacy programs and the programs that are using JIT, but we don't care about JIT right now. So yeah, in such a case, we could also store the whole region at the hard disk, and from time to time, it turns out that this is the unpacked malware. Okay, and another part, how to understand what is happening in the user mode while we are in the hypervisor level malware monitor. This is actually really, really tricky. So the first thing to describe is how Dragwolf hooks actually work. So we have this magical layer of mapping between guest physical memory and machine physical memory on the hypervisor. So what Dragwolf is actually doing is that when we hook something, the mapping is replaced from the page containing an original code to another copied page that contains the code modified in such a way that the breakpoint instruction is inserted whenever we request it. So this is how the virtual machine memory access looks like during execution. So by default. And when something inside the virtual machine wants to read this code, so this red page that is shown here, the view is quickly switched, and the mapping from the guest physical frame is switched to the page that is containing an original code. Then a single step in the virtual machine is performed, and then we are back to this kind of mapping. So when this would execute again, we will catch this breakpoint. And this way, these breakpoints are stealthy. So the virtual machine is not able to detect them, because once it would try to read this page, we are switched here, and it's fooled by the original code, but it's not actually executing. Okay, so this was the explanation about the stealth hooks, and now we would want to have the stealth hooks, but on the user mode level. And why? Because hooks on system calls are too low level for us. And as Adam said before, there are WinAPI functions that are not doing any system calls at all. And thanks to the user mode hooking, we would be able to hook the whole API, so we would have the full behavioral analysis. That's pretty cool. Okay, so what can be done since we have such hooks in place? Here is a simple demo. So let's say we are inside the Windows 7 VM. This is a clean Windows VM. We are building some simple program that would use script gen random in order to generate some random bytes, and then we just print these bytes. So look, here we have some random, again some random, some random, random. Okay, and now let's start Dragwolf with a special modification. We reset the program. Okay, and right now this is not so random, right? Yeah, so let's stop Dragwolf. and it's random again. So basically what Dragwolf did here is that it hooked crypt_gen_random function inside the guest VM, and it made it in such a way that it was not actually generating random, but returning zeros all the time. The problem is that this user mode part is much more tricky. So we could see most of the stuff this way, but we cannot add a breakpoint on a memory which is not yet mapped. And for user mode, it could happen from time to time. So this is a place we need to employ page fault injection through VMX, through libvmi. And this is how the DLL is hooked by Dragwolf right now. So I would state this is already implemented. So in order to reach an interesting DLL export, first we need to parse the PE header, like we were a normal Windows loader or something like that. Then we have to find image export directory. And then if the image export directory is not readable to us, and it could happen in a number of cases, Dragwolf needs to inject a page fault into the guest VM. So the guest VM would think that this portion of memory is needed immediately, and Windows would simply load it. And then we need to find the relative virtual address of the export that is interesting to us. And again, if this is not accessible, if the first instruction of the exported function is not accessible, we need once again to inject a page fault into the guest VM in order to force Windows to load this data. And what if the DLL would be purposely corrupted and the pointer, for instance, to image export directory would be invalid, or it would point to the kernel, or it would point to the middle of nowhere? So our injected page fault would crash our VM to which we are injecting this page fault. And the solution is that we need also to hook KI system service handler and pretend that nothing has happened. So the algorithm is like that. We need to check if we were recently injecting a page fault into this virtual CPU. And if it's not our fault, we resume the handler and let the VM crash normally. And if we see that the system service handler was executed right after we injected our page fault into the VM, we need to emulate the return instruction. So we need to read the saved instruction pointer from the stack, and we need to adjust the CPU context appropriately. So basically what we are doing here is that the hypervisor is trolling the VM by replacing some meaningful function with just return 0. So nothing has happened. We are continuing the execution normally. Yeah, another problem with such a hooks is that malware could attempt to override its own Win API function. And DLLs on the Windows are shared between processes, so copy on write occurs whenever the DLLs are overridden. And then the virtual page is still on the same virtual address, but it's moved to another physical address. So our hooks will not work in this case because they are on the physical level. Yes, so the reason here, the solution here is that we basically have to hook the copy on write handler, and the time for a short demo. Okay, so we have a clean Windows VM. We are starting Dragwolf against this VM and running our favorite game Heroes 3 complete. And we could see that the program on the host, on the Ubuntu host, is able to trace how much money we have in Heroes of Might and Magic 3. Okay, so we bought some building, the amount of money is lowered. Now we are passing the turn, so we got another 2,000, another 2,000, okay? And if we would like to control how much money we have in Heroes tree, we can make it using the soundbar. Yeah, so look at the amount of money. Yeah, and the trick is that nothing was modified in the VM itself. So this is a clean VM with the clean install of the Heroes of Might and Magic tree, and all the magic that is done from the host program, from the modified Dragwolf, which is intercepting basically everything that is happening and is changing the behavior in a way that is yeah, it works like in our demo. And another one, a very recent one. So we have a Dragwolf started and we run Internet Explorer inside the VM. And here we have the client random and master key dumped from this virtual machine. We could plug it to the Wireshark, and Wireshark will decrypt all the traffic that was recorded. Okay, and another feature that could be implemented using hypervisor level sandbox. Since we chosen to implement the sandbox on the hypervisor, we could use some features that are not available to kernel mode or user mode sandboxes. So we wanted to use Intel processor trace hardware feature. And this was the reaction of one of the Zen developers, since they realized that CertPL is implementing feature that they couldn't persuade Intel to do. Yeah, what could be accomplished when we have an Intel processor trace inside the hypervisor? So for instance, we could record the code coverage of the malware without actually hooking anything here. So we run our sandbox, we run our Windows 7 VM, then we start the hardware feature called Intel processor trace, and it basically records all the metadata about the execution. Then we could just take this metadata, parse it, and we see what branches were taken during the execution of the malware and what were not. These are the ones denoted with yellow color. So yeah, the arrows show what was executed and what was actually not executed. And yeah, using Intel processor trace, we are able to do that with a very small performance overhead, on only the overhead that is introduced by Intel processor trace itself, but it's very cheap feature, actually. Yeah, another thing that could be done with Intel processor trace is that we could record full user mode trace and correlate it with Dragwolf events. So the green part is the disassembly from the Intel processor trace. So this is the part of the code that was executed by malware process. And here we see the syscall instruction. So it somehow made a syscall. And in the red frame, we see what Dragwolf traced here. So we could combine these two information. And we see all the disassembly that was executed by the malware in the user mode. And when it enters the kernel mode, we see what particular event was logged by Dragwolf here. And then after the syscall was serviced, we see resumed, and we again get an Intel processor trace disassembly. So getting back to our example about obfuscated system calls, which were, I believe, in TrickBot, the malware has nowhere to hide practically, because even if it would implement some custom syscall gate in the user mode, we are able to trace it. So we would see from where the syscall was executed and what code was taken further. And as for the last demo, we can show
Python integration in the Dragwolf, in the Dragwolf, which we have written. This enables us to have a full IPython shell during which can fully interact with the VM and use all the capabilities of Dragwolf system right through your console. This is a regular Python shell you can use. You can perform all the actions normal regular Dragwolf C++ or C+ or C plugins do. You can handle callbacks in Python. You can hook user mode functions. And this is a demo where I have created a simple function which hooks internet crack URL A, then reads the argument from the stack, which is the URL, makes a call to URL house to see if the domain is malicious, and then prints the result. As you can see, this is Internet Explorer opening the MSN web domain, and you can see the requests on the left, which are being processed. You can clearly see that implementing a call, an HTTP call to URL house would be really annoying in C++, but in a Python console, it's just 2 lines of code. Of course, this comes at a performance disadvantage, but this is a nice tool to have. And out of the Dragwolf project, we have made a Dragoof Sandbox, which is a simple wrapper. Not as simple anymore, but it is still very easy to use. It's a wrapper around the Dragwolf engine. It provides a web interface, really streamlined and easy installation via downloading, I think, 3 deb files. It also has a queuing system built in and many more features. This is a screenshot from it. You can see these are the API calls that malware did together with the arguments it passed. Some of them are being parsed, like pointers to strings are already replaced with strings. And it is open source and free and ready to use for anyone. So grab it on the GitHub page.
Okay, and to summarize, yeah, here are the projects, all the projects that we were talking about, or most of the projects, I believe, are public and open source. So the Dragwolf engine is a creation of Tamas Lengyel and is available on GitHub. We were contributing a lot to this project. While Dragoof Sandbox is our own wrapper around Dragwolf, it's also available on GitHub for free. And it's also worth noting that Dragwolf is based on libvmi, which is also available publicly. Okay, and I would like to say thank you to all the CertPL reverse engineers, and particularly to Nazywam, Pesrock1 and MSM for many important remarks about how we should implement malware monitoring in Dragwolf and in Sandbox. And also to developers from CertPL, Chivai and Constante, for the further development and cooperation in Dragwolf and Dragwolf Sandbox projects. Also, thank you to Maciej Kotowicz for providing many good heuristics for memory dumping at the initial phase of the project. And as I said, to Tamas Lengyel for lots of helpful remarks during our research, and for the fact that he is a creator and maintainer of the Dragwolf project on GitHub. Yeah, so a bit of self-advertisement. We share a lot of data about malware, and white hat external researchers could join our system that is called MWDB, malware database. So if you work in a well-known company and you are doing white hat research, we strongly encourage to register and apply here. And basically, after registering, you get a lot of information about malware. So malware samples, the JSONs that we were showing previously, and a lot of more. Yeah, so basically, this was pretty much everything we wanted to say today. Once again, I encourage to check out the CERT Polska Dragoof Sandbox project on GitHub, and here there are our Twitter handles that you could follow in order to get updates and interesting stuff about this project. Thank you very much.
Thank you very much, Michał. Thank you very much, Adam. We wish you a lot of contributors. We want people to help you. We want everyone to join your effort and to try your project. Thank you very much for participating in the conference. Enjoy the evening. Thanks for the conference.